All right, let's get into the meat of Chapter 4. And in this section, we're going to talk about two types of geometries, kind of shapes of molecules. So we're going to talk about this thing called electron geometry or electron shape, and molecular geometry or molecular shape. So now that we can draw Lewis structures, we can use the information from Lewis structures to predict what the shape of the molecule is going to look like. So we're going to have these two geometries. We're going to have electron geometries and molecular geometries. So basically from the Lewis dot structure, we'll predict the electron geometry, and then from that we'll predict the molecular geometry. Electron geometry depicts how the groups of electrons are oriented in a molecule. So in our case, we're going to look at the central atom, and we're going to look at all the bonds to that central atom and all the non-bonding electrons on that central atom. Okay? The theory here is that the shape is going to be determined by this repulsion between these electron groups. Okay? So the electron geometry is the shape of these electron groups, all the electron groups around the central atom. Molecular geometry is basically we take the electron geometry, and in the electron geometry we look at the positions of the bonds or the bonding groups. Okay, and whatever shape that takes, that's the molecular geometry. So the real difference, if there's any difference between the electron geometry and the molecular geometry, is if there's any non-bonding electrons on the central atom, or on the atom that we're looking at, the molecular geometry will be different from the electron geometry. If, however, there are no non-bonding electrons on the atom we're looking at, then the electron geometry and the molecular geometry are the same because all the electron groups are bonds. Okay. So, when we're counting numbers of electron groups, we're going to look at the central atom, and we're going to count the number of bonding groups and the number of non-bonding groups on that atom. So when I say bonding group, a single bond is one bonding group. A double bond is one bonding group. A triple bond is one bonding group. Okay? Because it doesn't matter if it's single, double, or triple bond, those bonds exist between two atoms and they can't move anywhere else. It doesn't matter if it's a single, double, or triple bond. Those all count as one bonding group. And then we're going to have non-bonding groups, or lone pairs. And non-bonding groups are electron pairs on a central atom that aren't bonded to another atom. They're just on that central atom. Okay. So basically, all these groups are made of electrons. The bonds are electrons. The non-bonding pairs of electrons are electrons, and they all repel each other. Right? Their electrons are negatively charged. So we have this thing called valence shell electron pair repulsion theory, which is called VSEPR theory for short. And what it basically says is that all these electron groups around the central atom are going to repel each other. And they're going to repel each other to minimize the repulsion that they feel. Okay, so I've got electron groups, central atom, and they're going to move around until they get to a point where the repulsion is a minimum and they're kind of what's called lowest energy. All right, so let's take an example. I've got HCN here, and that's the Lewis structure. I'm going to look at the central atom only. I'm going to look at carbon. I'm going to figure out how things are oriented around carbon. First thing I have to do is count the total number of electron groups on the carbon. So I can see there's one electron bonding group, one bonding group, the single bond between the carbon and the hydrogen, and there's one bonding group between the carbon and the nitrogen, which is the triple bond. So there's two total groups. There are no non-bonding electrons on that carbon, so I'm only dealing with two electron groups. And there's two electron groups, the single bond and the triple bond, repel each other. They're electrons, right? So they repel each other, and when they repel each other, to minimize the repulsion, they go 180 degrees from each other. they go on opposite sides of the carbon, and that minimizes the repulsion. So if you look at our depiction here, that central atom in our case is the carbon, and these are the two electron groups. This is the triple bond on the right and the single bond on the left. If I move that single bond up a little bit, more towards the triple bond, it's just going to get pushed back down straight across from the triple bond. Okay, so because my two bonds are linear, they're a straight line with the carbon, we call that electron group geometry linear. Okay, so anytime we have two electron groups on the central atom, 2 and 2 only, the electron group geometry is going to be linear. All right, what if we go a step further? What if we have a molecule like this, which is formaldehyde? I'm looking at the central atom, which again is carbon, and I'm going to count the electron groups around that carbon. 1, 2, 3. So the bond between the carbon and the hydrogen is 1. The other bond between the carbon and the hydrogen is 2. And then the double bond with the oxygen is 3. There are no non-bonding electrons in there. So I've got 3 electron groups that have to get as far away from each other as possible. And I can see that this depiction over here shows what happens. I got the carbon in the middle. And then obviously I've got the hydrogen on one part, the hydrogen on this part, and then the oxygen over here. Or it could be, you could put them however you want. But they're equally distributed around the carbon. Okay? They're basically 120 degrees from each other, which just equally separates them from each other. That minimizes the repulsion that they feel from each other. So that shape is called trigonoplanar. So if I've got a central atom and 3 electron groups on it, they're going to make a trigonoplanar geometry. And then, so the other one we can look at here would be, this is ozone, O3. And I count the electron groups around that central oxygen. There's 1, the double bond. There's another one, the single bond. And now I have that non-bonding pair of electrons, what's called a lone pair. So I've got 3 electron groups around the central atom. And in this case, 2 of them are bonding groups and 1 is a non-bonding group. So if I use my little trigonoplanar thing here, I've got carbon in the middle, or excuse me, I've got oxygen in the middle now. I've got my 2 oxygens on either side. And then up here would be the lone pair, just the 2 dots. Okay, they each exist in kind of one of these lobes because they push away from each other. The lone pair is still a pair of electrons that's repelling and repelled by each of the electrons in the bonds. So again, I've got 3 total electron groups, except now I've got 2 bonding groups and 1 lone pair and non-bonding electron group. And it takes the electron geometry of trigonoplanar. So anytime you've got 3 electron groups, it's trigonoplanar. And then the last one we've got would be if we had 4 electron groups around the central atom, like this CH4, which is methane. We've got carbon with 4 hydrogens bonded to it. So I've got 4 total bonding groups around that carbon. No non-bonding groups, but 4 bonding groups. So that means I've got 4 things that are repelling each other and need to get away from each other. And to do that, the best way is to make this thing that's called a tetrahedral structure, or tetrahedral geometry, where I make this structure that's 3-dimensional now. The previous 2 were not. They were just 2-dimensional. This one's 3-dimensional. I can imagine making one where it's simply, kind of T-shaped where the carbon's in the middle, kind of like what the Lewis structure looks like. And if I do that, the distance or the angles between each of the hydrogens would be 90 degrees. In this structure, the tetrahedral structure, I can see that it's a bit bigger. Those angles are bigger, which means they're farther apart. So in this case, in the tetrahedral structure, the bond angles are 109.5. So quite a bit bigger than the 90 if we just kept the thing flat. All right, so any molecule where the central atom has 4 electron groups on it is going to have an electron geometry that's called tetrahedral. Now, it can be 4 bonding groups like we saw with CH4, or with ammonia here, the NH3, it can be 3 bonding groups and 1 non-bonding group. Or water, where there's 2 bonding groups and 2 non-bonding groups. Okay? It doesn't matter. When we're figuring out electron geometry, we're just counting the total number of electron groups. So all of those would be tetrahedral electron group geometry, because they all have 4 electron groups around it. All right. So if I make a nice little table like the one in your book, I can see that 2 electron groups around the central atom. The electron group geometry is linear. Now we want to know what the molecular geometry is. And remember, the molecular geometry tells me where the bonds are. And in the case of a linear molecule, like HCN, each of the groups around the central atom, each of the electron groups, is a bonding group. So that means the electron geometry and the molecular geometry are the same. That's because there are no non-bonding groups on the central atom in this case. So my 2 bonding groups, again, are 180 degrees from each other. So the electron geometry, which is just based on the total number of electron groups, is linear. And then my molecular geometry, which is just based on the position of the bonds, is also linear. Okay, let's go down to if I've got 3 electron groups. If I got 3 electron groups, we said that the electron geometry, the shape the electron groups take, is trigonoplanar, triangular plane. If all the groups are bonding and none are non-bonding, the molecular geometry is also trigonoplanar, because all the electron groups are bonding groups, all the electron groups are bonds, like we saw in formaldehyde. Okay. There are times when it could be 2 bonding groups and 1 non-bonding group, like in the case of ozone, which we saw earlier, O3, and in this case they have the sample S2. So S2 has this structure. It's got 3 electron groups, the non-bonding group, and then the 2 double bonds, which are each an electron group. So it's got trigonoplanar electron group geometry. But then if we look at just where the bonds are, it's just here and here, because there's the non-bonding group on top. So if we're looking at just the bonds, it's called bent, because it's bent. It's not linear, it's not straight, it's bent. So if I've got a molecule that has 3 total electron groups, 2 of those are bonding and 1 of those are non-bonding, the molecular geometry is bent. One more step. If I go to 4 total electron groups around the central atom, we said that will be a tetrahedral electron geometry, because there's 4 electron groups that have to separate themselves around the central atom, and it makes a tetrahedron. If all of those 4 groups are bonding groups, like in methane here, CH4, if they're all bonding groups, then the molecular geometry is also tetrahedral, because they're all bonds. Now, we could have a situation where 3 of them are bonding groups and 1 is a non-bonding group. For example, the ammonia that we saw. For the ammonia that we saw, we have the lone pair up there on the nitrogen. So the electron group geometry is still tetrahedral. 3 bonding groups, 1 non-bonding group, which is a total of 4. But my molecular geometry, where the bonds are, the shape the bonds take, is known as trigonopyramidal. Okay, so basically we have the lone pair on top here, and then we've got these 3 bonding groups, which are kind of that bottom piece of the tetrahedral. It's called trigonopyramidal because basically it makes a triangular pyramid. Pyramids are named by their shape of their base. So a triangular pyramid has a triangle as a base. And that's what this is. So if I've got a molecule that has 4 total electron groups, has a tetrahedral electron geometry. And it's got 3 of those 4 groups are bonding groups, and 1 is a lone pair. The molecular geometry is going to be trigonopyramidal. And then the last one, again, we have 4 total electron groups, except now we have 2 bonding groups and 2 non-bonding groups. An example here is water, where I've got oxygen in the middle. It's got 2 bonding groups to each hydrogen, each of the 2 hydrogens, and then it's got 2 lone pairs or non-bonding groups on it, so 4 total groups. Okay, tetrahedral. Electron geometry. The molecular geometry again is just where the bonds are. So in this case, we can see 2 of them are bonds in the tetrahedral and 2 are lone pairs. So we would depict it like this, and that's bent. It's not linear, they're not straight across from each other, but they're bent. Okay? So depending on the geometry, the geometry is determined by the structure. We get electron geometry from how many electron groups are around the atom we're looking at. And then molecular geometry is where the bonds are around that atom that we're looking at. Okay? I don't know what I have my picture here. So this is the same thing. It just goes what I just said, but it just gives you a little bigger image of just that particular electron geometry. Okay, there's the one for the tetrahedral. So let's practice. Okay, we need to draw Lewis structures and determine the electron and molecular geometries for the following molecules. So we need the Lewis structures before we do anything. So to draw Lewis structures, we need the number of valence electrons. So oxygen has 6. We have 2 fluorines, and each fluorine has 7. 2 times 7 is 14, plus 6 is 20. So we have 20 electrons that need to be in this structure. If I draw the skeletal structure, I'm going to draw the oxygen with each of the fluorines with 1 bond, showing that they're bonded together. When I do that, I use 4. I use 4 electrons to make those bonds. I have 16 electrons left. Now I put 6 extra electrons in the fluorines. They're the outer atoms. So they get their octet. And now they have 8 electrons around them. And to do that, I used 12 more electrons. And I have 4 left. And those 4, any left over, remember, go on the central atom. So the oxygen now has 2 non-bonding groups around it, or 2 lone pairs. Okay, so if we want the electron geometry, we count the total electron groups around the central atom. So oxygen's our central atom. We see we got 1 lone pair, 1 bond, another lone pair, another bond. Okay, so we got 4 electron groups around the central atom. When there's 4 electron groups, it takes the shape of a tetrahedral. It's tetrahedral. And then the molecular geometry, we have to look where the bonds are. So in this case, if I draw this, I'll put my F. If I draw it like a tetrahedral, F, over here is going to be my 1 lone pair, and up here will be the other lone pair. So I can see I've got 2 lone pairs, or 2 non-bonding electron pairs, and 2 bonding pairs. So this is going to be bent. Alright, NCl3. Counting our total valence electrons, nitrogen has 5, plus 3 times chlorine has 7. And there's 3 chlorines, that's why we're multiplying by 3. 3 times 7 is 21, plus 5 is 26. So we have 26 electrons. Drawing the skeletal structure, I've got nitrogen with 3 chlorines on it, like that. We use 6 electrons. We now have 20 left. Now we fill our chlorines, because they want 8 electrons. So we're going to fill our chlorines with using non-bonding electrons. And when I do that, each of the chlorines has now 8 electrons around it. 2 in the bonds and then 6 non-bonding electrons. I used 18 electrons to do that. So I have 2 left. Those 2 go on the nitrogen, because leftover electrons go on the central atom. We can see the nitrogen has 8 electrons around it. There's 3 bonds with 2 electrons each, so 3 times 2 is 6, plus that non-bonding group on top. So if we count the electron groups around that nitrogen, I get 1 non-bonding and then 3 bonding groups. So I have a total of 4. So the electron geometry, which I'm just going to call EG, is again tetrahedral, because there are 4 electron groups around it. Now my molecular geometry, which I'm going to call MG, shows where the bonds are. Now, in this case, if I draw it, I'm going to draw it like this. There's the 3 chlorines and then the lone pair up here. Oops, that was a lone pair. Or the non-bonding pair of electrons. Ugh, that just got worse. Let me get my eraser. Excuse me. Boop. Bring my pen back. And we're going to make those dots. Nice. Okay, so that's my structure. You can see that the bonds are down here. Kind of makes that trigonal pyramidal shape. So the molecular geometry is trigonal pyramidal. All right, last one, COCl2. In this case, it says carbon is central. That means that the 3 atoms, the oxygen and 3 chlorines, are bonded to it. Count the valence electrons. So carbon has 4, oxygen has 6, and then 2 times 7 because chlorines have 7. So 14 plus 6 plus 4 is 24. So 24 electrons. Put the carbon in the middle. Put the oxygen on top. Put each of the chlorines out to one side. It doesn't matter where you put them. That's just kind of where I'm putting them. We use 6 electrons. We have 18 left. So now I'm going to put 6 more on each of the chlorines and the oxygen. And when I do that, I used 18 electrons. So all my electrons are in there. There's none left over. So I know the chlorines and oxygen have 8 electrons, which is good. I need to check the carbon. I can see the carbon doesn't. It only has 6. It's got 3 bonds. So I can move a electron pair, a non-bonding pair in to make a double bond. And we're going to do that with the oxygen, because oxygen prefers to have a double bond in 2 non-bonding pairs. So when I do that, I get the structure that looks like this. The double bonded oxygen and the 2 chlorines with the 3 pairs of non-bonding electrons on them. Like that. Now, to figure out the electron geometry, we count the electron groups around the carbon. There's 1, there's 2, there's 3. So there's 3 total electron groups. For 3 electron groups, the electron geometry is trigonoplanar. And the molecular geometry, since there's no non-bonding electron groups on the central atom, all the groups are bonding, it's also trigonoplanar. Okay, so that's how you do this. Take the Lewis structure, take the atom you're looking at, count the electron groups around it, figure out what the electron group geometry is, or the electron geometry, and then from that figure out where the bonds are, and that's the molecular geometry.